Ancient sailors crossed entire oceans without any maps. They navigated the vast unknown using methods so clever, they essentially outsmarted the stars themselves. You are about to discover 22 unsolved puzzles from pre-modern navigation that continue to stump experts today. This journey will reveal how human ingenuity conquered the seas with nothing but observation and intuition. How did Vikings use a magic crystal to see the sun on a cloudy day? What secret patterns did Polynesian navigators read in the ocean's waves? By the end, you will understand the profound intelligence hidden in these forgotten arts. What do you think it truly means to find your way? A dense fog cloaked the Viking longship, swallowing the horizon and leaving the crew adrift in a world of grey. Yet they sailed on unerringly toward the distant shores of Greenland. Their secret was not a map or a compass, but a crystal clear as ice, known only as the Sunstone. Medieval sagas whisper of this magical tool, a stone that could reveal the hidden sun. Experts like archaeologist Thoria Johnson believe it was likely a piece of calcite or cordierite. These are not just pretty rocks, they possess a unique property called polarization. This means they can filter scattered sunlight, the kind that penetrates a cloudy sky, which our eyes simply cannot see. A navigator would hold the stone up to the sky and slowly rotate it. At a certain angle, the crystal would suddenly brighten, its internal light patterns snapping into perfect alignment. That alignment pointed directly to the sun's position, even at dawn or dusk when the sun itself was below the horizon. Experimental archaeologists have put this to the test. One modern sailor, using a crystal of Icelandic spar, a type of calcite, successfully navigated within just 5 degrees of true north under completely overcast conditions. It was a form of optical genius, a way of seeing the invisible. So why did such a powerful tool seemingly vanish from history? Was it too rare, too fragile, or was its knowledge a closely guarded secret that died with its masters? This puzzle of a crystal that outsmarted the clouds leads us to wonder what other tools navigators forged from the very world around them. While Viking navigators pierced the clouds with crystal light, another civilization was mastering the very fabric of the sea itself. For a Polynesian voyager, the ocean was not an empty void but a living, pulsing highway. They could steer an open canoe across thousands of miles of open Pacific by reading the ocean's swells as if they were a map etched into the water. This profound art was known as wave piloting, a skill so refined it feels almost like magic to the modern mind. It was not magic, however, but a lifetime of accumulated observation, passed meticulously from one generation to the next. The principle is deceptively simple. Just as a rock in a stream disturbs the flow of water, an island disrupts the deep ocean swells. Waves bend or refract around the landmass, creating a unique interference pattern that radiates outward far beyond the horizon. A master navigator learns to feel these subtle shifts through the movement of the canoe, sensing the distinct wave signature of an island he cannot yet see. He would lie in the hull, feeling the rhythm and direction of the swells through his entire body, his senses tuned to the ocean's whispers. This knowledge was not gained overnight. Training began in childhood, with elders teaching students to recognize countless wave patterns in coastal waters, long before they ever ventured into the deep blue. This wave reading was combined with an encyclopedic knowledge of star paths, the flight patterns of birds, and the color of the sky, creating a complete mental navigation system. It was this system that allowed the Polynesian people to discover and settle the most remote islands on Earth. scattered across an ocean larger than all the continents combined. The power of this tradition was stunningly proven in 1976 with the voyage of the Hokulea, a replica of a traditional Polynesian double-hulled canoe. Guided by the Micronesian master navigator Maupiailug, who possessed this ancestral knowledge, the Hokulea sailed from Hawaii to Tahiti without any modern instruments. For over a month, Mau read the waves and the stars, feeling his way across 2,500 miles of open ocean to make a perfect landfall. What secrets did he perceive in the ocean's rhythm that our satellites and sensors cannot detect? Modern science can model wave refraction, but it struggles to replicate the intuitive, embodied wisdom of a navigator who feels the sea as an extension of his own being. This aquatic wisdom speaks to a deep, almost forgotten connection with the natural world, a puzzle that leads us from the ever-shifting sea to the seemingly permanent land, where another mystery is set in stone. These silent stone sentinels stand as one of prehistory's most enduring riddles. Scattered along ancient coastlines from France to Scotland, vast fields of megaliths like the thousands at Karnak form eerie, parallel rows that march across the landscape. While many see them as purely ritual sites, a compelling theory suggests they were the original sea marks, a massive, permanent navigation system carved from the land itself. Imagine a Bronze Age sailor approaching a foggy, unfamiliar coast. By sighting along two specific stones, he could align his vessel with a safe, deep water channel, avoiding the treacherous shallows that lay on either side. The stones acted as giant calipers, their positions encoding vital local knowledge. The Callanish stones in Scotland offer a stunning clue, their central monolith and surrounding circle precisely aligned with the moon's most extreme northerly rising, an event that occurs only every 18.6 years. This was not just ceremony, it was a sophisticated calendar. Knowing the moon's phase and position was crucial for predicting tides, the very lifeblood of coastal travel. A navigator could use such an alignment to know when a high tide would flood a dangerous reef, allowing safe passage, or when a low tide would strand him on the mudflats. The sheer effort to erect these monuments speaks to their immense importance. Quarrying, transporting, and erecting multi-ton stones required a coordinated society, one that clearly depended on the sea. This was an engineering project on a scale that rivals our modern lighthouses, a communal investment in safe passage. Yet the debate remains fierce. Were these places temples, navigational aids, or both? Perhaps for ancient peoples the distinction was meaningless. Navigating the physical world and connecting with the spiritual one were intertwined. The true puzzle is how the builders encoded such complex, multi-layered information into silent stone without a written manual. The knowledge had to be perfect, repeatable, and passed down through generations purely by oral tradition. This stone-based enigma, a puzzle of sight and alignment, leads us to wonder if ancient navigators used another, more ephemeral sense to find their way. What if the next great secret of pre-modern navigation was not something you could see, but something you could hear? From the silent alignment of standing stones, we turn to a world of sound. The coastlines of the ancient Mediterranean were not just a visual landscape, but an auditory one. Sailors navigating by night or through fog learned to listen to the land, using the echoes from sea caves to map the invisible shoreline. This acoustic navigation finds a haunting echo in Homer's Odyssey, where the lethal song of the sirens may have been a mythologized version of a very real phenomenon. The theory suggests that navigators would shout or blow a horn toward a cavernous cliff face, then measure the time it took for the sound to return. A quick, sharp echo meant they were dangerously close to hidden rocks, while a longer delay indicated a safer, deeper channel or a wider bay. Experts in the field of archaeoacoustics, like Stephen Waller, have studied how specific cave shapes and the depth of the water at their entrances could amplify and shape these returning sound waves. The science is based on reflection. Sound travels, hits a surface, and bounces back. A deep, hollow cave creates a long, low rumble, while a shallow overhang produces a short, crisp snap. The water itself acts as a sound reflector, so the acoustics change with the tide, providing even more information. This turned entire coastlines into audible landmarks. Oral traditions from various cultures describe caves that sang or groaned, and Greek lore is filled with tales of sailors using such sounds to avoid perilous places like the cliffs of Scylla. In modern experiments, researchers using replica environments have confirmed that with practice, a person can indeed judge distance and even identify specific coastal features by echo alone. This auditory art was a perfect complement to stellar navigation, a way to fix your position when the skies were dark and the land was shrouded. So why is this skill almost entirely lost? In our visually dominated world, we have forgotten how to listen to our environment in this profound way. These echoes held secrets of the sea's mood and the shape of the land, a language of sound that has fallen silent. This puzzle of hearing the land leads us to an even more subtle art, the ability to smell your way home from miles out at sea. A seasoned sailor standing at the prow of his ship could close his eyes, breathe in deeply, and detect the distant scent of land long before any hint of it appeared on the horizon. This was not superstition, but a finely honed navigational skill documented in logs from medieval Europe to the Arabian Sea. Navigators learned to identify the specific smells carried on ocean breezes, the earthy aroma of damp forest soil, the sweet fragrance of flowering mangroves, or the sharp, resinous scent of pine. These odors were tangible evidence, organic compounds like terpenes released by plants, traveling for miles over the water under the right wind conditions. Arab traders navigating the Indian Ocean towards the Spice Islands would note subtle shifts in the air's quality, a sudden complexity that signaled they were on the correct course, their target still invisible but now perceptible. The human nose, while often underestimated, is capable of extraordinary detection. Certain molecules are remarkably stable and can be carried vast distances, acting as an early warning system. The key was training. From a young age, aspiring navigators were taught to associate specific smells with particular lands. A navigator from the Marshall Islands, for instance, would learn that the unique scent of pandanus trees could be detected from over 10 miles downwind, a fragrant thread leading directly to a low-lying atoll. This skill was often combined with the observation of seabirds. A bird flying out from its roost might carry the scent of land on its feathers, or its direction of flight at dusk would point the way home. In persistent fog, when neither the sun nor the stars were visible, the sense of smell became a critical tool for survival. It was a biological compass, a direct line to a world they could not yet see. How did these sailors refine this sensory skill to such an astonishing degree of precision? It required a lifetime of attentive practice, a deep, quiet listening to the environment that modern, instrument-reliant navigation has all but erased. We now prioritize the visual and the digital, leaving this olfactory map, this invisible pathway of scent, largely forgotten. This puzzle of smelling the unseen land forces us to reconsider the limits of our own senses and leads our gaze upward to the subtle colors painted across the sky at dawn and dusk. A deep red sunset was far more than a beautiful end to the day. It was a vital meteorological report. Across centuries and cultures, sailors learned to read the language written in the colors of the sky, a skill codified in rhymes like "Red sky at night, sailors delight." Red sky in morning, sailors take warning. This was not mere folklore, but a practical application of atmospheric science, understood long before the principles were formally named. The secret lies in how sunlight scatters as it travels through the atmosphere. A red sky at night typically means the sun is shining through a mass of stable, dry air high in atmospheric pressure, which scatters the blue light and allows the red wavelengths to pass through. This stable air was often moving from the west, promising fair weather for the next day. Conversely, a red sky in the morning suggests that this same stable air has already passed eastward, and moisture-laden, low-pressure systems which can bring storms are likely following behind. Pale, washed-out yellows and greens, however, were a more urgent warning. These hues indicated a high concentration of moisture and dust particles in the air, a telltale sign that a storm might be brewing. The knowledge was nuanced and regional. A Mediterranean sailor might interpret a specific shade of orange differently than a North Sea fisherman, because the typical weather patterns and airborne particles in each region created distinct optical signatures. This art was fully integrated with reading wind patterns and cloud formations, creating a holistic short-term forecast. Christopher Columbus's crew relied heavily on these observations during their transatlantic voyages, using the sky's palette to anticipate squalls and avoid disaster when they were utterly alone on an unknown ocean. They possessed a deep, intuitive understanding of atmospheric optics, seeing the sky not as a static canopy but as a dynamic, living map. What subtle gradients of color and light could they perceive that we, distracted by modern forecasts, simply overlook? This visual mastery of the heavens finds a parallel not in another celestial body, but in the flight of creatures much closer to Earth. The flight of a bird could mean the difference between life and death for a lost mariner. Viking sagas and Pacific Islander lore are filled with accounts of ships adrift, their crews placing their trust in the innate sense of direction possessed by migratory birds. At dawn, watching a flock's determined flight path was like reading a living map drawn across the sky. Species like the Arctic tern, which undertakes a pole-to-pole migration spanning tens of thousands of miles, were particularly reliable indicators. Seeing these birds meant you were within their range, and their direction of travel often pointed toward the nearest landmass or a chain of islands you could not yet see. This was not a matter of blind faith, but of acute observation. Navigators learned to decode specific avian behaviors. A bird flying high and straight was likely on a long-distance journey, heading directly for a nesting ground. A bird flying low, frequently diving to feed, suggested a rich feeding area which often existed close to shore. The time of day was also critical. Many seabirds fly out to sea to fish at dawn and return to land at dusk. Spotting a stream of birds flying in a consistent direction at sunset was one of the strongest possible signals that land lay in their path. In Polynesia, the magnificent frigatebird was a key guide. These birds, which famously avoid landing on water, would only be seen flying near their home islands. Spotting a frigatebird meant an island was almost certainly within 100 miles. This knowledge was meticulously cross-referenced with the stars. A navigator would note the bird's direction, then confirm it by checking the position of a known star path once night fell. Early texts hint that Irish monks seeking solitude may have followed puffins across the North Atlantic to discover Iceland, trusting the bird's homing instinct over their own limited understanding of the open ocean. How did these sailors achieve such a deep, symbiotic understanding of avian patterns? It required a lifetime of watching, learning not just about the birds but from them. They saw the birds as partners in navigation, creatures whose ancient instincts were more reliable than any human-made tool. This organic approach, a dialogue with nature, stands in stark contrast to our modern, self-contained systems. Why have we abandoned this feathered guidance, this silent partnership with the natural world? The answer may lie in our desire for control, for instruments that give us answers without requiring us to truly listen. This profound trust in a creature's path leads us to the next great mystery, one that required sailors to listen not to birds, but to the wind itself. A sailor's hand raised to the wind could feel more than just a breeze. It could read a story of pressure and distance written on the air itself. Long before meteorology had a name, navigators were master decoders of atmospheric flow, discerning subtle shifts in wind direction, temperature, and humidity that revealed their position and predicted the weather for days to come. This was the secret of wind pattern decoding, an intuitive science refined over countless lifetimes at sea. The great wind systems of the world, like the reliable trade winds or the seasonal monsoons, were not obstacles, they were predictable highways. Arab D. How captains in the Indian Ocean did not fight the monsoon. They planned their entire trading year around its clockwork reversal. Their logs meticulously recorded how the winds shifted with the seasons, carrying them to Africa on one leg of a journey and back to India on the next. The principle is rooted in the planet's own rhythm, the combination of Earth's rotation and the uneven heating of its surface creating vast, circulating cells of air. An experienced mariner could feel a change in the wind's character, a slight increase in humidity or a shift of just a few degrees, and know that a storm was brewing long before the clouds appeared, or that a current had carried them toward a specific, unseen coast. This knowledge was so vital it was etched directly onto their charts in the form of wind roses, elegant diagrams showing the direction and frequency of the winds for any given stretch of ocean. On the ship itself, telltales, small ribbons tied to the rigging, served as real-time indicators of airflow over the sails, allowing for minute course corrections that maximized speed and efficiency. This intuitive grasp of aerodynamics often proved more valuable than a simple compass heading. During Magellan's famed expedition, his pilots navigated the treacherous straits at the tip of South America in conditions where clouds hid the stars for weeks. They relied almost entirely on feeling the wind funnel through the narrow passages, using its changing direction and force to map their way through the labyrinthine channels. What innate understanding of atmospheric dynamics did these sailors possess that our modern tools, for all their precision, cannot fully capture? They were not just observing the wind, they were conversing with it, feeling the planet's breath as a tangible force. This mastery of an invisible guide leads us to an even deeper mystery, one hidden within the Earth's own magnetic heart. A navigator's most trusted tool might not have pointed north at all, but toward a hidden deposit of iron ore or a uniquely magnetic stretch of coastline. This is the enigma of magnetic stone navigation, where lodestones were used for far more than just finding direction. These naturally magnetized pieces of magnetite, often called leading stones, possessed a secret that went beyond simple polarity. Ancient Chinese and European texts suggest that experienced sailors could detect tiny, local variations in the Earth's magnetic field using these stones, deviations caused by undersea mineral deposits or geological formations. The historian Joseph Needham documented that Chinese compass makers were aware of magnetic declination, the difference between magnetic north and true north, centuries before it was formally defined in the West. How did they use this knowledge? A navigator would first calibrate his lodestone by noting its alignment against a known star like Polaris, establishing a baseline for true north in that region. Then, as he sailed, he would watch for any subtle shift in the stone's indicated direction. If the lodestone began to point slightly east or west of its expected alignment with the stars, it signaled a local magnetic anomaly. This was not a random error but a clue. In areas like the Baltic Sea, rich with iron deposits, these magnetic signatures became recognizable landmarks on an otherwise featureless watery map. A specific deviation might indicate the ship was approaching a particular island chain or a known or rich bay. Norse sagas that mention sunstones might sometimes be describing lodestones used in tandem with solar readings, creating a dual verification system. Legends of magic stones that pulled ships toward safe harbor could be folk memories of this practice, where a captain followed a familiar magnetic tug toward a hidden inlet. Finding a lodestone artifact on a sunken ship is not just evidence of a compass, but a potential key to a lost navigational chart written in the Earth's own magnetic field. How did these early mariners so accurately correlate these invisible magnetic cues with precise geographic locations? It required generations of painstaking observation, of sailors comparing their lodestone's behavior with every headland and island, slowly building a mental library of the sea's hidden magnetic personality. This profound sensitivity to the planet's invisible forces presents a stark contrast to our next puzzle, which relies not on the Earth's deep magnetism, but on the most transient of guides, objects floating freely on the water's surface. A piece of waterlogged oak scarred by shipworms and trailing seaweed was more than just flotsam to a pre-modern sailor. It was a floating message. In the vast blue desert of the open ocean, any piece of driftwood was a vital clue, a natural buoy that spoke of distant shores and the powerful currents that connected them. This was the practical science of driftwood navigation, a skill that required an encyclopedic knowledge of botany and oceanography. Medieval European logs are filled with careful notes on the type, size, and condition of wood encountered at sea. Finding a fragment of a northern pine, for instance, indicated the ship was within the influence of currents flowing from Scandinavia or North America. Conversely, a piece of tropical mangrove signaled an approach to equatorial coastlines. The wood's condition was its own timestamp. A log still bearing bark and fresh-looking fractures had entered the water recently, suggesting land was near. A piece that was heavily waterlogged, saturated with salt, and covered in barnacles and algae had been traveling for months, perhaps even years, carried across entire ocean basins. Navigators learned to read this marine growth like a calendar, estimating drift time and, by extension, the distance to the wood's likely origin. This knowledge was passed down orally, with masters teaching apprentices to identify countless tree species by the grain, color, and density of the wood, even when waterlogged and worn. In the Pacific, where currents like the Kuroshio are powerful and consistent, driftwood patterns became predictable pathways. Polynesian navigators correlated specific types of waterlogged debris with the flight paths of certain land-based birds, creating a multi-layered confirmation system. If they saw a particular bird and a specific type of wood, they knew with high confidence they were on the correct bearing for a specific island group. A clear historical example comes from 15th century Portuguese records, which describe sailors using driftwood to confirm their approach to the Azores Islands. As they sailed westward into the Atlantic, encountering distinctive types of European driftwood carried by the Gulf Stream and North Atlantic drift served as a floating confirmation that they were on the right track, long before the islands themselves rose from the horizon. What profound ecological insight did these mariners possess that allowed them to read the sea's scattered debris like a living map? They saw the ocean not as empty space, but as an interconnected system of rivers in the sea, each current carrying its own unique signature of life and land. This practice of reading nature's floating clues reveals a mindset that looked for guidance in the most humble of objects, a perspective that leads our gaze from the water's surface back to the heavens, to a celestial body used in a way that defies conventional wisdom. The moon's slow drift against the starry backdrop held a secret key to one of navigation's greatest challenges, finding east-west position. For a pre-modern mariner, the moon was not just a night light. It was a slow-moving clock hand sweeping across a dial of fixed stars, a celestial mechanism for estimating longitude. This method, known as lunar distance, was a computational marvel that some cultures may have attempted centuries before John Harrison's famous chronometer offered a mechanical solution. The principle was elegant in theory but daunting in practice. By measuring the precise angular distance between the moon's bright limb and a specific, well-known star like Aldebaran or Spica, a navigator could determine Greenwich Mean Time, the time at a prime meridian. Comparing that time to the local time found by observing the stars revealed the longitude difference and thus how far east or west the ship had traveled. Arab astronomers from the medieval period, such as those in the House of Wisdom, developed complex lunar ephemerides, tables predicting the moon's precise position for years in advance. These tables were the heart of the system, a pre-computed almanac against which a single observation at sea could be compared. The measurement itself was the first great hurdle. Navigators used instruments like the cross staff, a simple wooden rod with a sliding crosspiece. They would align one end with the moon and the other with the chosen star, the sliding piece marking the angle between them. This had to be done on a rolling ship deck, a task requiring immense skill and a steady hand. Even a tiny error in measurement, a fraction of a degree, could translate into a longitudinal error of dozens of miles. This inherent inaccuracy, combined with the need for complex, error-prone calculations, is why the method never saw widespread use in the age of sail, ultimately being superseded by the marine chronometer. Yet, there are hints that simpler forms of this knowledge existed elsewhere. Polynesian navigators, with their profound understanding of celestial movement, likely used the moon's path across the sky as a rough longitudinal guide within their vast mental star compasses. They did not need complex math, but an intuitive sense of how the moon's relationship to certain stars changed as they sailed east or west. How did pre-modern cultures approach this immense computational challenge without extensive written records? The answer lies in a different kind of record-keeping, a living, oral tradition where this precise stellar and lunar knowledge was memorized, recited, and refined across generations. It was a collective human brain acting as a living almanac. This celestial puzzle of the moon's measured dance leads us from the cold mathematics of the cosmos to a phenomenon that transforms the sea itself into a living, glowing map. The dark sea itself could catch fire, painting a vessel's wake with a ghostly, shimmering light. This was not a supernatural event, but a natural marvel meticulously observed by navigators who learned to read the ocean's own living lanterns. They called it sea fire, a phenomenon we now know as bioluminescence, caused by trillions of microscopic organisms called dinoflagellates. When disturbed by a ship's hull or the churn of a current, these tiny creatures emit a brief, brilliant flash of blue-green light. To the untrained eye, it was simply a beautiful spectacle, but to a master mariner, these patterns of cold fire were a dynamic chart of the unseen world below. A sudden, intense glow in the water ahead could signal a school of fish, but more importantly, it often indicated turbulent water flowing over a submerged reef or a sharp, rising shelf. The light would flare with extraordinary brightness in these shallow areas because the disturbance was greater, agitating more of the luminous life. Conversely, a soft, steady, and widespread glow suggested deep, calm water, a safe passage through the darkness. Medieval Arab and Malay pilots in the Indian Ocean became particularly adept at this. Their logs speak of navigating treacherous island chains like the Maldives by following specific trails of light, using them to locate the deep water channels that snaked between the coral atolls. Folklore from the region is filled with tales of spirits guiding lost ships with a gentle radiance, a clear mythologizing of this very real skill. The light acted as a temporary, living buoy system, visible only to those who knew how to interpret its fleeting messages. This required a specific kind of perceptual training. A navigator had to learn the difference between the random sparkle of a lone wave and the consistent, organized flow of light that revealed a current's path or an underwater hazard. He had to understand how the phase of the moon affected the visibility and how to distinguish the light of dinner flagellates from the glow of other creatures, like certain jellyfish. It was a skill of instant pattern recognition, honed over years of night sailing. How did these sailors quiet their minds enough to perceive such subtle, ephemeral clues in the midst of a vast, dark ocean? They were reading a language of light written on the water itself, a temporary map that appeared only when disturbed and vanished just as quickly. This mastery of living light reveals a depth of attention to the marine environment that we have almost entirely lost. It leads our gaze upward once more, from the ocean's transient glow to the fixed points in the sky, but not to the stars we all know. A master navigator's star map was not drawn on parchment but etched into memory, using stars far beyond the familiar shapes of the zodiac. This was the secret of non-zodiacal star paths, a celestial navigation system so precise it turned the entire night sky into a personalized compass. Polynesian and Carolinian voyagers created mental star compasses centered on stars like the brilliant Sirius or the southern giant Canopus. Each of these stars did not just shine, it pointed. Its rising position on the eastern horizon was one bearing, and its setting point in the west was another, creating a spoke-like grid of directions across the ocean. A navigator bound for a specific island would memorize the sequence of stars that passed directly overhead on that route, following this celestial highway from one zenith star to the next. The stars low on the horizon were especially crucial, as their altitude above the sea remained relatively constant for a given latitude. By tracking these horizon stars, a voyager could effectively sail a line of constant latitude, a technique known as latitude sailing, ensuring they would eventually run directly into their target island. The knowledge required was immense. Navigators learned the seasonal changes for dozens of stars, knowing which ones were visible at different times of the year and how their paths shifted. This was not a static map, but a dynamic, rotating one they carried in their minds. The anthropologist David Lewis, who sailed with these navigators, documented their ability to use star holes, fleeting gaps in the cloud cover. In a matter of seconds, they could identify a single star and its position, instantly correcting their course before the clouds swallowed the sky again. This entire complex body of knowledge, a living astronomy, was transmitted orally across generations through chants, stories, and rigorous teaching. Carolinian navigators, for instance, could make the incredibly difficult open ocean voyage from Guam to Yap, a journey of over 800 miles, using these star paths alone. How did they maintain such precise mental charts without a single written ephemeris to correct errors? It was a collective human achievement, a library of the sky built from memory and shared with poetic precision. This stellar expertise, a puzzle of memory and the heavens, leads us to wonder if navigators could sense another, more physical clue rising from the sea itself, a change in the very temperature of the water. A sailor's bare hand plunged into the ocean could feel the warmth of a distant tropical sea. This was the subtle art of sea temperature sensing, where the skin itself became a navigational instrument. Early Atlantic logs described seasoned mariners discerning minute changes in the water's feel, variations imperceptible to anyone but the most trained observer. They were literally feeling the boundaries between different water masses, the fronts where a warm current like the Gulf Stream met the colder surrounding ocean. In persistent fog, when every other sense was rendered useless, this tactile information became critical. A sudden, slight warming of the water could confirm they were riding the Gulf Stream north, a massive river within the sea that could add several knots to their speed, while a drop in temperature warned they were drifting out of its beneficial flow. Medieval Basque whalers were masters of this, tracking the thermal signatures that led them to the richest whaling grounds. The science is one of heat and movement. Ocean temperatures are not uniform, they shift with depth, creating layers called thermoclines, and they are carried vast distances by powerful currents. A navigator learned to associate specific temperature bands with specific locations, his hand calibrating to differences of just a degree or two. This skill was often paired with other signs. The appearance of certain birds or a particular type of driftwood, combined with a familiar water temperature, created a multi-sensory confirmation of their position. Norse explorers venturing into the icy waters of the North Atlantic would have been acutely aware of the dangerous chill emanating from a nearby iceberg, a cold plume extending far beyond the visible hazard, allowing them to steer clear long before the ice itself loomed out of the mist. What incredible tactile acuity did these sailors develop, a sensitivity we have now outsourced to digital sensors. They were reading the ocean's own pulse through their skin, a direct physical connection to the planet's circulatory system. This profound attunement to a physical force leads us to an even more imperceptible influence, one that pulls not on the skin, but on the very mass of the ship itself. A ship could feel heavy, as if the sea itself was clutching at its hull. This strange sensation, reported in old mariners' tales, points to a 15th puzzle, the enigma of gravitational anomaly detection. While they had no instruments to measure it, some theorists propose that pre-modern navigators, deeply attuned to their vessels' every movement, might have sensed the faint tug of underwater mountains. Dense seabed features like seamounts or ridges create tiny local increases in gravity, variations so subtle they are measured in milligauls, a unit far smaller than any human could consciously perceive. Yet, through a lifetime at sea, a captain might notice his ship responding differently, a slight, inexplicable sluggishness in otherwise calm waters. A pendulum, perhaps hung in the captain's quarters to steady a lamp, might show a minute persistent deviation. Even the humble lead line, a weighted rope used for sounding depths, could feel subtly different as it sank through water influenced by a stronger gravitational pull from the seafloor below. Legends from various cultures speak of heavy seas guarding sunken treasures, waters where ships moved with unnatural slowness. These stories could be folk memories of sailing over such gravitational highs, where the increased mass of the seabed exerted its invisible influence. Ancient Phoenician sailors, masters of the Mediterranean, may have instinctively avoided areas where their agile vessels felt oddly burdened, unknowingly steering clear of submarine ridges that posed a navigation hazard. This was not a calculated science, but a deep, embodied intuition. A navigator's entire being was a sensitive instrument, calibrated by years of experience to feel the sea's most imperceptible moods. How many safe passages were made because a captain trusted a gut feeling that something about the water was just not right? This profound sensitivity to physical forces we now need satellites to detect reveals a layer of environmental awareness that is almost unimaginable today. It suggests that the ocean held secrets not just on its surface, but in the very pull of its depths. From this puzzle of feeling the unseen mass below, we are drawn back to the surface world, to a challenge that demanded a different kind of perception entirely. A dense fog could turn the world into a shapeless, silent prison, but for a skilled coastal pilot, it was a chamber of echoes waiting to be read. This was the art of fog echo ranging, a primitive form of sonar that used the human voice and the returning sound waves to map the invisible. In regions like the fog-shrouded coasts of Newfoundland or Brittany, sailors learned to shout or sound a horn, then listen intently for the echo's return. The time it took for the sound to come back revealed the distance to a hidden cliff face, while the quality of the echo hinted at the size and shape of the obstacle. A sharp, quick snap meant a nearby sheer rock wall. A longer, rumbling, and more diffuse echo suggested a distant, sloping beach or a wide bay. The acoustics behind this are straightforward yet powerful. Sound travels through fog with remarkable clarity, as the water droplets in the air have little effect on its propagation. When that sound wave hits a solid object, it reflects, carrying information about that object back to the listener. Medieval Breton fishermen developed specific calls, sequences of horn blasts that were unique to their villages. This allowed them to not only gauge distance, but also identify other friendly vessels in the blinding mist, preventing collisions and coordinating their movement. Training in echo discrimination began in childhood, with elders teaching the distinct sound signatures of every headland, cave, and sandbar along their home coast. A navigator had to learn the difference between the echo from a single, menacing pinnacle and the complex reverberations from a cluster of islets. This auditory map was deeply integrated with tidal knowledge. The same cliff would produce a different echo at high tide when water filled its base, compared to low tide when the sound would reflect off exposed rock and wet sand. Folk tales from these regions are filled with stories of spirits answering calls from the fog, a clear mythological layer over this practical, life-saving skill. So why has this audible art, this ability to hear the shape of the world, faded into near oblivion? In our modern reliance on radar and GPS, we have sacrificed a direct sensory conversation with our environment. This mastery of sound in the opaque air leads our curiosity from the shrouded coasts to the clear night sky, to a celestial puzzle that used planets not as guides, but as messengers. Venus, blazing in the pre-dawn sky, was more than a beautiful morning star to a Mayan or Babylonian astronomer priest. It was a celestial clock. While most sailors relied on the fixed stars, a select few mastered the wandering paths of the planets, using them as dynamic checkpoints on their mental star charts. This was planetary positional logging, a layer of celestial navigation so complex it bordered on an arcane science. Ancient records from these cultures contain incredibly precise tables of planetary movements, predicting the positions of Venus and Mars with astonishing accuracy for decades in advance. At sea, a navigator could use this knowledge to verify his course. If Venus appeared in a part of the sky where the tables said it should not be, he would know his estimation of longitude was likely wrong. This was especially crucial during the twilight hours, when the brightest planets were visible but the fixed stars were still too faint to see clearly, offering a precious window for celestial fixes. The development of planetary almanacs was the key. These were not simple charts, but complex ephemerides compiled by generations of temple scribes, detailing the planet's retrograde loops and changing speeds against the backdrop of the zodiac. For cultures where navigation was intertwined with cosmology, this was a form of ritual navigation, a way of aligning a voyage with the perceived order of the gods themselves. How captains in the Indian Ocean, for instance, may have used the cyclical appearances of Venus to confirm they were on the correct monsoon-driven route between East Africa and India, their celestial knowledge passed down through guilds of pilots. The complexity, however, was its greatest barrier. A sailor had to memorize not just the paths of stars, but the ever-changing dance of multiple planets, a computational burden that required a lifetime of study. So what shortcuts did they employ? They likely focused on key events like a planet's first visibility in the morning or evening sky, or its conjunction with a particularly bright star. These moments were easier to remember and served as clear, singular milestones in a long journey. They might also have used simple mnemonic devices or rhyming verses to encode complex orbital periods. The true puzzle is how this profound astronomical knowledge, so carefully recorded on clay tablets and in stone observatories, was translated into a practical skill for use on a rocking ship in the middle of an open ocean. Why would a navigator go to such lengths when the stars seemed sufficient? The answer lies in the pursuit of absolute certainty in an uncertain world, a desire for multiple, overlapping confirmations of one's path. This celestial verification using wandering stars leads our gaze from the sky's moving points of light back down to the ocean, to a puzzle written not in light, but in 1,000 subtle shades of blue. The ocean's surface was a living palette of blues and greens, each hue a message about the world beneath the waves. A master navigator could read these colors like a map, discerning depth, seabed composition, and the promise of fish from the subtle variations in the water. In the clear Pacific or the sun-drenched Mediterranean, this was the daily practice of ocean color interpretation, a visual science as critical as any chart. A sudden shift from deep, dark blue to a lighter, brilliant aquamarine signaled a transition from profound depths to a submerged coral reef or a rising shelf, a warning to steer clear. A murky, greenish tint often meant a silt-laden river outflow or a nutrient-rich upwelling zone, where cold water from the depths brought a feast for marine life and, consequently, an excellent fishing ground. The optics behind this are a matter of light absorption and reflection. Sunlight penetrates the water, and the different wavelengths are absorbed at varying rates. In deep, clear water, the blue wavelengths are scattered and reflected back, creating that iconic deep blue. In shallower areas with a white sandy bottom, the light reflects off the seafloor, creating a brighter turquoise color. Sediment or dense populations of phytoplankton, tiny plant-like organisms, absorb the blue light and reflect green, coloring the water accordingly. Training to distinguish these hues was a lifelong discipline. Elders would take apprentices to different coastal areas, pointing out the specific shade that indicated a sandy bottom, perfect for safe anchorage, versus the darker, greener tint of a seaweed-covered rocky outcrop that could tear a hull apart. This knowledge was so vital it was sometimes encoded directly onto medieval portolan charts, with notes in the margins describing the color of the water for specific bays and anchorages. This skill worked hand in hand with the sounding line. A sailor would see a promising greenish hue, then confirm the depth by casting the lead line, its tallow tip bringing up a sample of the seabed sand, shell, or mud to match the visual clue. Ancient Greek texts, including Homer's description of the wine-dark sea, may not have been merely poetic. Some scholars argue this phrase could denote the deep, pure indigo of very deep, safe passage water, as viewed in the specific light of the Aegean. The greatest challenge was standardization. How did a sailor know that the green he saw at noon under a blazing sun was the same dangerous green of a shoal he remembered from a cloudy dusk? The answer lay in constant comparative observation. They used the color of the sky and the angle of the sun as a consistent backdrop against which to judge the sea, their eyes becoming finely calibrated instruments. This visual mastery, a profound dialogue with light and water, represents a pinnacle of conscious observation, yet it leads us to a final, deeper mystery, one that resides not in the trained eye, but in the uncharted territory of the sleeping mind. A veteran navigator asleep in his swaying hull did not rest from his work. He continued it in the realm of dreams, Across Polynesian and Norse sagas, leaders reported visions that charted courses to unknown shores, a phenomenon modern science might call navigational intuition. This was not magic, but the mind's ultimate synthesis of a lifetime of sensory data. The brain, having spent decades observing the subtlest patterns in wave rhythms, distant bird calls, and shifts in wind pressure, could process this information subconsciously, weaving it into a powerful, undeniable feeling of the correct path. These hunches often arrived not as vague notions, but as vivid, specific dreams. Anthropologists studying oral traditions note that in these cultures, such dreams were rarely dismissed as fantasy. They were respected as messages from ancestors or gods, a direct line to collective knowledge. Rituals to induce these guiding visions were common. A Polynesian navigator might isolate himself before a long voyage, fasting and chanting to clear his conscious mind and allow this deeper wisdom to surface. The role of this intuition was most critical in exploratory voyages, where no pre-existing star path or wave pattern could be memorized. The Icelandic saga of Eric the Red provides a striking example, recounting how dreams and visions directly influenced the course that led to the discovery of Greenland, guiding settlers through treacherous, ice-filled seas they had never seen before. How was such a subjective feeling validated? Ultimately, through successful outcomes. A captain who followed a dream and found land cemented the practice's validity, his success becoming part of the oral lore that trained the next generation. The cognitive process at work is a profound fusion of observation and instinct, where the human brain becomes a biological supercomputer, running environmental models in the background and delivering the results as a gut feeling or a nighttime vision. This mental mystery, the ability to feel one's way across an ocean, demonstrates a layer of human consciousness deeply interwoven with the natural world. It also leads our curiosity to a final, almost philosophical puzzle, one that questions the very nature of perception by asking what happens when the sky and sea become a single, mirrored realm. A navigator's world could shrink to the single, shimmering path of a star reflected on a perfectly black sea. When clouds obscured the sky itself, the ocean's surface became a secondary celestial map, its mirrored calm revealing star paths that the naked eye could no longer see directly. This was the subtle art of reading Starlight Reflection, where the water itself transformed into a vast, dark compass. The phenomenon relies on a simple principle of optics. On a night with no moon and a glassy, calm sea, the water's surface acts as a near-perfect mirror. A bright star like Vega or Sirius does not just shine down from above, it also shines up from below, its reflection creating a perfect, elongated glimmer stretching toward the horizon. By aligning the bow of his vessel with this line of reflected light, a mariner could maintain a steady bearing even while staring down at the water, his course locked onto a celestial guide he could not see in the sky. The key was identifying the true signal amidst the noise. A master navigator trained for years to distinguish these clean, linear reflections from the random, scattered glare of bioluminescence or the deceptive shimmer of a distant weather front. He learned that only the brightest stars created a reflection stable and long enough to steer by, and that this technique worked best in enclosed, calm bodies of water like the Red Sea or the Arabian Gulf. Arab D. How masters navigating the treacherous coral reefs of the Red Sea reportedly used this method on overcast nights. They would identify the reflective path of a specific star known to lie over a safe, deep water channel, then follow that liquid highway of light through the labyrinth, keeping them off the razor-sharp coral that lurked just beneath the surface on either side. This demanded an incredible stillness both in the water and in the observer's own perception. The slightest breath of wind would shatter the mirror, and a moment of inattention could cause a sailor to confuse a reflection with a faint light on a distant shore. How did they achieve such a disciplined focus, training their eyes to see order in what most would perceive as mere sparkle on an inky void? It was a practice of profound patience, a testament to the human ability to extract absolute direction from the most ephemeral of clues. This silent guidance from starlit water represents a perfect fusion of sky and sea, a navigational puzzle that leads our senses toward a final, elemental mystery written not in light, but in the very air we breathe. A column of distant smoke on the horizon was a living landmark, a signal of land written on the air itself. For sailors navigating the dense island chains of Indonesia or the Aegean, volcanic vents or village hearths produced towering plumes that served as temporary but vital beacons across dozens of miles of open water. The direction of the smoke was the first clue, pointing straight to its origin, but its color and behavior told a deeper story. A thick, black, roiling column indicated a large, intense fire, perhaps from an active volcano, while a thin, grayish-white plume likely signaled a smaller, controlled source like a settlement. The smoke's movement was a direct reflection of the wind patterns aloft, allowing a navigator to read atmospheric conditions far beyond his own position. Spanish explorers sailing toward the Canary Islands documented using the persistent smoke from the volcano on Tenerife as a homing signal, a fixed point in an otherwise featureless seascape that guided their final approach. The science lies in particulate dispersion. Smoke rises and spreads based on the heat of its source and the stability of the air it moves through. A stable, steady plume suggested consistent winds and fair weather, while a plume that quickly flattened and dispersed indicated turbulent, shifting air, a potential warning of an approaching storm. This skill was seamlessly woven with wind reading, the navigator's eyes moving from the sail to the distant haze, correlating the local breeze he felt with the grander flow visible in the sky. Yet this method carried inherent danger. Approaching an active volcano for a bearing meant sailing toward potential eruption, ash fall, and unpredictable waters. Minoan sailors of the Bronze Age may have routinely used the volcanic island of Thera, modern Santorini, as a navigational marker, its plume a familiar guide until its catastrophic eruption around 1600 BCE reshaped the entire archipelago. What intuitive grasp of atmospheric chemistry did these mariners possess, reading the composition of the air to judge distance and stability? They understood that the sky was not empty, but filled with traces of the world, a testament to their profound connection with every element of their environment. This final terrestrial clue, a puzzle of reading the air's own impurities, brings us at last to the most rhythmic of all the mysteries, the pulse of the ocean itself. The rhythm of the ocean was not just felt but memorized, an intricate clockwork of water and gravity held entirely within a navigator's mind. For Celtic and Scandinavian sailors, the tides were not a mystery but a predictable force, their complex patterns for specific coasts internalized with breathtaking precision. These mariners learned to read the lunar phases and seasonal cycles as a direct key to the sea's behavior, anticipating exactly when a treacherous strait would flood with deep, safe water, or when a river mouth would run high enough for a laden vessel to cross its bar. This was the enigma of tidal cycle memorization, a living almanac of the sea's pulse. The mechanics are driven by the gravitational pull of the moon and sun, a cosmic dance that creates the familiar ebb and flow. An experienced navigator did not need to understand the physics, only the correlation. He observed that a full moon or a new moon brought the highest high tides and the lowest low tides, the spring tides, while the quarter moons brought the gentler neap tides. Over years, he correlated the moon's position in the sky with the specific water level at his home port and along familiar trade routes. This immense body of data was far too vast for simple recall, so it was encoded. As marine historians like Geoffrey Chaucer have noted, this knowledge was often locked into rhymes, songs, or chants. These were not simple poems but sophisticated mnemonic devices, where each verse contained tidal data for a specific day of the lunar month or for a particular headland. A single line could tell a pilot the exact hour a tidal race would begin to run in a narrow channel, or when a hidden sandbank would be safely covered by 10 feet of water. This oral transmission was a matter of life and death. In places like the Thames estuary with its vast, shifting mudflats and complex currents, medieval English pilots used this memorized knowledge to navigate without any charts. They knew that attempting a crossing at the wrong state of the tide meant certain grounding and potential shipwreck. Their strategy for landing was entirely dictated by this internal clock, timing their arrival for the moment a hidden cove became accessible or a beach offered a gentle slope for pulling a boat ashore. In the foggy, high-latitude waters where the sun and stars were often hidden for weeks, this tidal sense became their primary guide, a rhythmic force they could trust even in total blindness. How did they achieve such precise mental calculations of these immense rhythmic forces? It was a symphony of memory, observation, and oral tradition, a collective intelligence passed from one generation to the next. Having explored these 22 puzzles, from the sunstone's crystal light to the memorized rhythm of the tides, we are left not with a collection of curiosities, but with a profound realization about human ingenuity. These were not random tricks, but a cohesive, multi-sensory system for understanding the world. Each method represents a different way of seeing, hearing, and feeling the environment, a deep dialogue between humanity and the elements. They remind us that navigation was once an art, a holistic practice that engaged the entire being. In an age of satellites and digital charts, these forgotten arts challenge our definition of intelligence itself, asking if true knowledge lies not just in the data we can store, but in the wisdom we can feel. These 22 puzzles are not isolated curiosities. They are the individual instruments of a grand symphony. Each method, from smelling the land to feeling the tides, reveals a common genius, the profound integration of multiple senses into a single, cohesive navigation system. Pre-modern mariners did not fixate on one tool. They wove together a tapestry of inputs. The stars gave them a course, but the waves confirmed it. The wind provided power, but its subtle shifts warned of weather. The flight of a bird, the color of the water, the echo off a cliff, all these clues were cross-referenced in the navigator's mind, building a robust, adaptable mental map of the world. This was not a collection of tricks, but a holistic way of thinking, a deep and continuous conversation with the environment. The true innovation was not in any single device, but in this powerful synthesis. When clouds hid the stars, they listened to the waves. When fog blinded them, they felt the water's temperature. Every limitation spurred a new way of perceiving, forcing an ingenuity that turned the entire natural world into a guide. This approach relied on three profound human capacities: keen observation, vast memory, and the careful transfer of knowledge across generations. A master navigator's mind was a living library, its contents memorized through chants, stories, and years of apprenticeship. This intergenerational wisdom ensured that hard-won insights were not lost but refined over centuries. What does this multifaceted intelligence teach us today? In an era of technological dependency where a single GPS signal can fail, their methods offer a powerful lesson in resilience. Modern fields like ecology and artificial intelligence are now grappling with the same challenge: how to process complex, multi-layered environmental data to solve problems. The Polynesian navigator who combined bird behavior with wave patterns was practicing a form of deep ecological literacy that we are only now beginning to appreciate with advanced sensors. Their legacy is a testament to human adaptability, proving that our greatest breakthroughs often come not from overpowering nature, but from learning to listen to it more closely. This holistic wisdom, born from necessity, invites us to reconsider the very nature of intelligence, suggesting that true understanding lies in connection, not in isolation. The 22 unsolved puzzles of pre-modern navigation form a legacy of profound human ingenuity. From the Viking Sunstone that captured hidden sunlight to the memorized rhythm of the tides, these ancient mariners did not conquer the sea by overpowering it, but by listening to its every whisper. They transformed the natural world into a living map and compass, proving that curiosity and adaptability can overcome even the most daunting challenges. These enigmas are more than historical footnotes, they are an invitation. They ask us to look up from our screens and remember the wisdom embedded in observation, in the feel of the wind and the color of the water. Which of these puzzles captured your imagination the most? Was it the Polynesian wave pilot feeling his way across the ocean, or the mystery of the standing stones silently guiding ships to safe harbor? Share your thoughts in the comments below. I would love to hear which journey resonated with you. If you enjoyed this voyage into history's hidden wonders, please subscribe for more deep dives. Until next time, may your own journeys, wherever they may lead, be guided by the timeless wisdom of the past.